In this video, we're going to do one final example. The example is of SF6. We're going to demonstrate the hybridization process that occurs and explain the bonding using valence bond theory, electron promotions, if applicable, and hybridization. So we'll start off by drawing our Lewis structure for SF6. Let's do that. And we're going to predict the hybridization of SF6 right away, essentially, just using the shorthand technique we learned earlier. So here's SF6. It's going to be one of those expanded octets. This, this, that, this, and this. And we'll put our lone pairs. And now we have our Lewis structure for SF6. There's no reason why that line there, the extra line there, that line is longer than the others. It's just a bad drawing on my part. But let's go ahead and figure out the hybridization of S by counting the electron regions. So we have S, P1, P2, P3. Then we go to D1, D2. So that's S, P3, D2. So we have an Sp3 D2 hybridization for sulfur. And now let's go and determine the hybridization for fluorine. So we'll just count the electron regions around fluorine. And since they're all the same, we just have to do this once. So this is an electron region, so Sp1, P2, P3. So fluorine would be Sp3 hybridized to best explain its shape. So I'm just going to erase that now since we did our shorthand technique. It's not really cheating, it's just looking ahead of time so we know what to look for when we're drawing. And what we're going to start with is we're going to start with our fluorine. So fluorine, we'll do an energy level diagram. And it has 9 electrons. So we have 1s, we have 2s, and then over here we have 1, 2, 3. These are 2 p's here. So it would look something like this. Notice that this is the electron that will likely be used over here for bonding, the one at the very end that's alone. We want to show hybridization. So even though the fluorine just needs to form one bond and it already looks good as is, we're still going to show the hybridization because it's going to better predict and allow for maximum overlap in its hybridized shape. So what we're going to do is we're going to make the valence electrons, the 2s and the 2p over here, mix. We're not going to do an electron promotion. We're not going to throw an electron up into the 2p level because we already have enough single electrons for bonding. We're just going to allow these to mix or hybridize. Mix, you can say, or hybridize, same thing. And we'll get an intermediate level of energy. And we'll place our electrons. So we have the 2s ones that were there are now here. The 2p's are now over here. And the single 2p is over here. And since this is made from the S and the P, there's 1s and 3 p's. These are all sp3s. They're still in the second energy level, so they're all 2 sp3s to be more specific. So 2 sp3s to be more precise. I'm just going to write them as sp3 here, sp3, sp3. So these are hybridized orbitals for the fluorine atom. Now keep in mind, you would be doing this times 6, right? Because there's 6 fluorines. But we just have to write times 6, and then we should be good with that. So now we're going to go and we're going to draw the orbital level diagram for sulfur and show its hybridization that we determined to be Sp3 D2. So for sulfur, we have This, that's our 1s. We have our 2s over here. We then have our 2p. We have our 3s. And then we have our 3p. So this is our 3s, 2p here, and then our 3p. So that's 10, 12. So we should have 4 more electrons for 16 electrons. And that's our sulfur. Now, yes, we typically fill up the 4s next, but right now we're in the third shell. So in the third shell, don't forget we also have our D. We also have our D level orbitals. They're empty, but we have our 3 Ds there. Now, we want to look at sulfur and see how many electrons it needs for bonding. Notice it's forming 6 bonds, right, with the sulfur. So it needs 6 single electrons for bonding. And if you look in the third shell, sulfur does not have 6 single electrons. It only has 2. But we can create, or we can generate 6 single electrons through electron promotion and hybridization. Notice we can make an electron jump from here to here, and another electron jump from here to here. So we can do electron promotion, and then we can make them mix at a somewhat intermediate level between all of these here. So somewhere around here. So we're going to have the 3s mixing with the 3p's mixing with 2 of the d's. So it's going to look like this. We have the 3s from before, the 3p's that are still there because they're all involved in that mix there, and then 2 of the d's. And then the other d's remain unhybridized. So the ones that are left over are these unhybridized ones here that were not used. So we have an electron from the 3s, then we have an electron from the 3p, the other 3p, the other 3p, and then the ones that were promoted up are over here. And then the other ones here, they remain unhybridized. We don't really need to draw them in for now, but they remain unhybridized, so they're still 3Ds. So I want you to notice that this is made from an S, 3Ps, and 2 Ds. So we call that Sp3 D2, Sp3 D2, Sp3 D2, Sp3 D2, Sp3 D2, Sp3 D2. So these are now going to form the overlap with the Sp3 electron from the fluorine down below there. So essentially this is going to happen 6 times. So we have an overlap between one of the fluorines like this. Another fluorine would overlap with 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 this. And another fluorine would overlap with this. And so that's all the bonding explained there. And the other thing you can explain as well are the lone pairs around the fluorine. The lone pairs around the fluorine are simply these Sp3 lone pairs that you see over here. So each of those drawings would correspond to those Sp3s. And each of these direct overlaps here, they would be sigma bonds. So each of these little overlaps I did is a sigma bond. So really we have 6 sigma bonds forming here. 6 sigma bonds that form around the sulfur when it overlaps with the fluorine atom orbitals. So to finish off, we can do our drawing. We'll do sulfur, and we'll make its little Sp3 D2 balloons. Like that. And don't forget they each contain one electron. And we'll make it pointing up. And then we'll do our fluorines. And don't forget they have the 4 hybridized orbitals. And so this is its opposite spin electron there. And these ones here are the lone pairs. And so you would draw this same thing all around to do all those overlaps. For example, I would do another one over here. This will be the lone pair, lone pair, lone pair in there. And then this region of overlap here would be one of the sigma bonds, like that. And you do the same drawing all the way around to show the direct overlap forming the sigma bonds as you see there. And the sigma bond here forms between the 2 sp3 of F and the 3 sp3 D2 of S. That's how the sigma bond is forming. And then the lone pairs, so this is a sigma bond formation. The lone pairs are 2 sp3 of F, of the F atoms. So what we've seen here is an example of an Sp3 D2 hybridization. We had to essentially draw the fluorine and show its hybridization. It already had enough electrons for bonding, but the hybridization still occurred without a promotion because it had enough electrons for bonding. So we showed the mixing happened, and it was made from an S and 3p, so it's sp3. And then here's our single electron that was used for that direct overlap of the sigma bonding. And then we drew sulfur. Sulfur, you'll notice, was missing electrons for bonding. It needed 6 electrons because it formed 6 bonds here, and we only had 2. So what we had to do is we had to do a promotion. So we promoted them up. We couldn't promote them to 2p to the p because if we did that, you just have another pair, and you wouldn't have really created much more in terms of single electrons. So we had to free up some space to make single electrons. What we could do is access the d orbitals within the third shell here. So we could promote them up to the d. So we made this one jump to our d over here, and this one jump to the d over here. And now what we had is a mix of the s, the p, the p, the p, and the 2 d orbitals there. The other 3 d orbitals were not really involved in that, so we just left them as is, or unhybridized. So essentially we mixed a s, 3 p's, and 2 d's to make sp3 D2. And these are still at the third energy levels, just kind of in between the p, the d, and the s. But since it's still at the third energy level, they're called 3 sp3 D2. And we were able to predict this hybridization without having to do all this drawing. In case there's a multiple choice, you just need a quick answer by simply counting the electron domains. And remember, the first domain you count is S, the second is P, the third is P, the fourth is P. So if you only have 4 electron domains, it's sp3. If you have 2 electron domains, that's sp2. If you have 2 electron domains, it's sp. And again, like I said, if you had 4 domains, that's sp3. And if you have more than that, so if you have 5 domains, that's sp3d, and 6 domains, that's sp3d2. So if you had 6 domains, like we have here, we have sp2, 3, so sp3, d1, d2. sp3d2 if you have 6 domains. And it's a nice quick way to calculate to determine hybridization of an atom. And remember, electron domains are single bonds, double bond, triple bonds, they count as one domain. So whether it's single, double, or triple, we just didn't see double, triple yet because that involves a different type of overlap, which is not sigma bonding. There is sigma bond still in there, but there's another type of overlap as well that happens in addition to sigma bond. And then the other thing that counts as an electron region are lone pairs. So a lone pair is one electron region. So for example, here we have one electron region, S, two electron regions, P, three electron regions, P2, four electron regions, P3, Sp3 for fluorine. So that's how to approach that, to do a quick hybridization check before you go and do your diagrams. And it helps you to see what you need to do in those diagrams if you do that ahead of time. So it's not really cheating. It's just informing yourself beforehand so you know what to do ahead of time. And so one more thing I would recommend you do before you end this lesson is you try to do the hybridization representation for the molecule of Cl2. We did molecules like this before, like F2, without looking at hybridization. But now that we understand hybridization, how it better predicts the shape of molecules, you're in a position to explain the hybridization of the Cl atoms in the Cl2 molecule. There's a video in your handout that says Dr. B video. It's listed next to the practice. You can watch that for additional clarification and to check your work after you've tried the hybridization of Cl2. A good hint is to draw the Lewis structure first, and then see if you can draw hybridization diagrams to show where overlap will happen and where sigma bonds form, and also to show how to account for lone pairs in your energy level diagrams.